Hi, this is Roman Budek. So I'm going to demonstrate using the MKE15 board, one from another, one set up as a master, one set up as a slave. And what it's going to do is transfer a number of bytes from one board to the other board and verify that one I2C communicates to the other. This is a great debugging tool because you can use the demo board as a way of just sending a stream of data to your board to see if you can receive all the packets error-free. I'll also monitor them with a sniffer and a logic analyzer to verify that the traffic is going smoothly. But this is a great simple code that you could go and run on your board and verify that your system is working. So what I have, I will start the board here now, the slave board, and in my console window, I will be able to see what it's receiving. So I'm going to start up a debug session and then plug in the master board. You'll see a picture shortly of what the connections are like. So one MKE15 talking to another, and I'm starting the debug session. All right, and I'll start running it. It is now waiting for the data. I'm plugging in the master board now. And you can see all the data is being received, and it finished the example. So it sent I2C data, and it was received from one board versus the other. And two different versions. You can run it from a console or run it from a just a regular terminal window. And a great debug tool. Hello, Roman Budek. So another way to debug the I2C is I want to use a known good board, which was our I2C evaluation board, and write a script to see now if the MKE15 running the software, master slave software running as a slave, will it recognize a known script? So on the left side of the screen is my MKE15 board. On the right is a script that I wrote with the NXP evaluation board. And so what I'll do is go ahead and run it. I'm sorry, it was already debugging. So all I have to do is run it. And now it's waiting for the data pattern, but instead of having another MCU board send the commands, what I'm doing is setting and running the scripts. So what I'll do is I'll send all, and you'll see that the data is recognized. So it sends out whatever sequence. I'm not sure why it sends out a 0, 1, a 20, and then it starts sending out the hex numbers 0, 1, 2, 3, and it recognizes them. I don't get a readback function working on that because it looks like I have to put quite a long pause. But nonetheless, it does receive it right, and the logic analyzer confirms that the data was sent out correctly. So another way to debug the I2C would be to hook up the customer board to receive data and generate it from this board rather than the MCU. Hello, this is Roman Budek. So I'm going to show how to check out what the data logging is with this low-cost I2C sniffer called I2C driver. And what I'm going to do, my setup is two NXP development boards, an MKE15. One is set up as a master, one is set up as a slave. This will send data from the master. When I push the reset switch up here, it'll transfer 32 bytes of data over the I2C clock. Data and ground are the only three wires connecting everything, but it'll connect up here to the slave board. The slave board will read the data. The USB port is going to be connected up to show me that it is in fact reading this data in the proper sequence, and then it responds back by sending back all the data over to I2C back to the master to verify what data was sent and sending it in sequential order. It's going to write to address 7E, which is the slave device here. The protocol sends a byte 01 first and 20, which is 32 in decimal. That means 32 packets of data it's going to send, and then a 01 at the end. Hooking up all in parallel off of that, I'm tapping in the I2C driver board, which has the data log capability, and comparing it to what the logic analyzer captures to see what the differences are with how it captures the data. The physical setup is, again, here is my master board with the reset switch that I'll hit, slave board running three wires connecting SDA, the data, the clock, and then the ground as well. So the first pin on this connector is set up to be clock, then data, same hardware here. We can see I use better colors here. So clock is yellow, data's green. I've got a multi-point tap here so that then my I2C driver board can capture data. My logic analyzer probes are connected up to here. Logic analyzers in the background, connected up, clock data ground. And the USB cable from here comes into the port on my computer so I can monitor to see what data it says it reported. I think I mentioned already that's the data capture device, sniffing device, and logic analyzer. And this will be the slave that'll execute the software by running MCU Expresso code on it. Here's a close-up of the connection. So 4 connections, 2 female, 2 male. Allow me to plug in 1 pin into the board. It changes color here. It goes to purple to my second board. This one changes to gray. Multi-tap here, so 1 tap can go to the sniffing device, and then a bare lead is sticking out to allow the logic analyzer to clip on. You can see the logic analyzer clipping on here, and then a ground wire as well. So to see it running, the first issue that I have is that the I2C software requires to execute 3 times. You execute it the first time, it loads up 2 versions of this code that really don't do much, and then you execute it a third time, a second time, and it loads 2 versions of it. 1 disappears, and you're left with 3 versions running, and that third version running appears to be working fine then after that. So it does find COM38. By the way, I do have the right serial port. If I use my diagnostic port, I could see that the device, which is this UART device, that's the only one that's on there. It's using the FTDI driver instead of the generic, but either one has that same symptom where I have to run multiple versions of that capturing tool. The first thing to note is that I have to disable the pull-up resistors because they're already enabled on my board. And I'm going to set the speed limit, make sure it's 100 kilohertz. And I'm going to enter capture mode. When I do that, it'll ask me for a file name. And I will go to the next version. I'll call it log 7. As soon as I hit save, my board on the display of the I2C driver changes to C, so it's going to capture data. The next thing I'm going to do is make sure that my logic analyzer is armed. I have clock and data with the right colors on it, I2C protocol analysis on it, and timing I'm doing on the clock so that I could see how fast the clock is running. I have to arm my software on the slave so that I can capture if it's actually receiving the data or not. So it ended, the software runs once, and here it will, I think I let it Let me restart it just to make sure, clear out all the samples, kill the debug. And so what I will do is load the software, and it will execute. Starting in the console window, I'll see the response that I'm getting. So right now it's flashing the micro, discovered a target. And there we go. Now it's ready to execute. So I will execute, and it's waiting for the data. So it's going to repeat back when it gets the data and when it returns it back to the master. It's going to be a little hard to time this here, right? But there's my console window. And let me see if I can lower my logic analyzer here. And I have my window set up here for capture. The display is saying C. So in fact, it is in capture mode. So what I will do now is I'm going to capture data. Make sure it's set up right. So I have it. Yep, 10 mega samples, 500 kilohertz sample rate. I could go lower. Hide this so I can see more of the data. And what I'll do is I'll start the logic analyzer first, and then let you know when I push the reset switch. When I push the reset switch, you'll see the data coming here on the serial port and being captured by the logic analyzer. So I'm starting to run. I push the button now, and it shows right here I'm capturing some kind of data, and sent it, received all this data, sent it back on the master, and it set it to the logic analyzer and to my capture. So, sorry, I got too many devices on my USB port, so I don't have a scrolling mouse. So this would be the data that was sent, and I'm going to zoom in on it. So the data should have been sent in one continuous block. I can see here, address decoded, sending all my sequential data. All right. So it's writing to address, does it start a frame? That's a write acknowledge here. Then the slave doesn't acknowledge. The address 7E says it's present. It writes the protocol is to send a 01 first hex, then a 20, which is 32 bytes and decimal of data. Each packet gets acknowledged individually. It sends the data sequentially, and then it does a read. But let's see how the data log looks. So first thing I have to do is go to this tool and the capture mode, and it says 58 events were saved to log 7. Let's pull those up. Log 7 it was. Timestamp matches. And so it starts out right. It writes to 126, which is 7E in hex. It's acknowledged, writes a 1, which is the protocol that we saw in the logic analyzer, and then it writes a 32 or a 20 hex, which is exactly what we saw happening here. So that matches up. So it's sending a 01020, which is the 32 hex. Then it writes a 0001. Each packet is acknowledged. So that's lining up. Let's see, it's writing 3, 4. Now this is weird. It's saying after 4 that it did a read, and that in fact did not happen. Did 4, 5, 6, 7, 8, 9 are all writes. It is properly saying that they were acknowledged. So that's good. Now it's saying that it tried to read after it wrote wrote a 4, tried to read, and the start doesn't make sense because that's not in there. And then 4, 5, 6, so it's saying it repeated 4. So somehow it's skipping a byte or something. 5, 3, 7, 8, 9. So it does skip numbers, but it does kind of sequentially go on, and that's not what happens. Now it's saying I got to knack all of them. were acknowledged, including 14. So if I go along here, you can see that in fact every single packet gets an acknowledged, 11, 12 gets a valid acknowledge. And then what it should show is now it writes a 0, 1, and then waits for a read. I don't see that at all. I see it stop. Now this might be what it's trying to line up. It wrote to address 70, which is 126 hex, writes to 1, which I see here. The start, so it did capture this stop event over here. It did capture the writing. It wrote the 0, 1. Now it's going to do a read. So it missed a few stuff here, missed a bunch of data, got the reads mixed up. But let's go ahead and zoom out here and scroll to when it does the reads. Oh, and you can see my timer set up between packets. So here it waited 90 microseconds to send it. Now it's going to wait 83 milliseconds before the next set of data. So this would be my reads. And I can see now, in fact, it's going to do a read operation. So I'd imagine that over here, that's what the log is showing, a read. Now a 0, 1, so it's going to read back the data with acknowledges. So other than I missed a few stuff here, now it's going to read them back. A 0, 1, 2, 3, 4, 5, 6 with acknowledge, 8. Now it's saying it skipped ahead to 16, which it does not. Now these packets are spread out a little bit further. You can see about 76 milliseconds between packets. So I will scroll across and it reads them actually about 2 bytes at a time. So here it transmitted my 001, which we saw here was showing up properly with acknowledge. So 0 acknowledge to, we want to check what happens after packet 8. So here's 001. Should be my 1 and 2, 2, 3. Sorry about the delay here. My next ones, 4 and 5. The next set of data. Six, 7, so over here, 6, 7 with an acknowledge. Now it's going to say about 8 it's going to complain about, so capture that data. Actually, that came a little quicker, 60 milliseconds on that one. As you can see, I don't see any problem with the logic analyzer. Read an 8, got an acknowledge, read a 9, got an acknowledge. So have to figure out what this is saying, but it looks to me like this data logger is getting an error. Now with this software here, I can see the tabular view as well, decoder output. And so I could see that it's saying, at least the logic analyzer is saying that it did read wrote a 1, a 20, 1, 2, 3, 4. He codes it in the tabular format. Logic analyzer sees it just fine. So at this point, I'd have to say that the data logger has some issues with it besides running. As I mentioned, you have to execute it multiple times, but the data log that it stores is quite problematic. Also, it doesn't give you any kind of timing data with this data here. Oh, so I wrote a 1F. There we go. We did a stop condition, then we did a start condition, and then I'll start reading. If I wanted exact timing values with this, I could also set it up to, notice, I could set it up to read timing values in here as well. Timing, so that's showing I2C commands, but I could go down and pull out timings out of this tabular format. So at this moment, it looks like this tabular format's much more useful than this I2C driver. Now, if I look at the I2C driver, it is kind of useful, I guess, with one or two messages. It does mess up also when I look at the display. It'll show the last 2 or 3 commands graphically, but it will miss the address. It writes down the wrong address that's being received. So I don't know how to trust that data. If there's any other questions, let me know. Well, this is Roman Budek, so I'm going to use this sniffer, I2C sniffer, to see if it has some value over a logic analyzer. This time what I'm going to use is some hardwired I2C devices. Last time it was MCUs emulating I2C. This evaluation board, which unfortunately is no longer sold, it was used to verify compliance with a bunch of I2C devices that you either did in a breadboarding area here, plugged on with headers, expansion cards, or in this case, soldered down devices. So the one we're going to use as a slave device is the IO expander PCA 9672. That's soldered down. The address on the silk screen is printed here is address 044 hex. And the master device in this case is an MCU running the commands and also interfacing through the USB port. The connections are shown here. Down here, a blow up of this connection here. So I'm going to be using SDA 1 and clock and data from it. Pull-up resistors are enabled for that port over here. Clock and data, clock is yellow, data is green, and there's my ground connection. And so the first thing I'm going to do is bring up the software. Well, first of all, so again, the I2C driver, in fact, I have to reset the board from the last time I did the video. You can see that it has to run 3 instances. So again, you run it first, you have to end the task for all of them, and then reset the board, plug the board back in, and then run it once. It runs 2 instances, execute it a second time, and it runs 2 more instances, but one of them disappears in this third instance, or I guess the second instance here is the one that's actually running 1 out of the 3. But minor irritation, it does run, and then now it does find the boards. So when I go into here, it does find the port COM38. Incidentally, now, because the board is connected, it is showing the devices that are found. However, you have to switch between shifted and unshifted addresses. So 44 hex is 22 in whatever mode that is, unshifted mode. So you have to do that translation. And then once again, showing that the software driver I'm using is the FTDI driver. That seems to be the most stable one. That's the board, and using FTDI bus, most stable for getting readings. And the evaluation board is using generic HID USB bus. There's some newer drivers, but I didn't want to muck around with those. So we've got that set. Let's try to execute the software for the board. Bring up the software. If there's anything hooked up wrong or a connection wrong, you'd notice it'll take a real long time to come up. But now it came up. It was obviously working now. The first thing that it does tells you the board was detected, and it did a transmit, meaning it's on a reset to all other devices. Irritating thing is it defaults to 1 megahertz, so you always have to set up 1 kilohertz. If for some reason you unplug and plug the cable back in, it may be telling you that it's 100 kilohertz, but it's not. So before you run it, make sure you just set it to 100 kilohertz. Now here's the block diagram showing everything on the board. So that map that my device is finding over here are devices that are all soldered down on the board. The 9672, as I mentioned, is this 22 hex over here. And then other ports are ones, empty ports that you plug cards in. These labeled ones are plugged in. And so I'm going to use a device, and it's an I/O expander, 8-bit 9672. And the particular one that's of interest is the 44 hex. All right, and what I will do now, there's no MCU Espresso, but there still is my logic analyzer, which I will bring up over here. So running this time, lower the sample count to 2 mega samples, so I don't need that much memory stored on it. Here was the part about shifted and unshifted. So actually writing the address 44, this was a previous capture I did. It showed up a different address. This 22 is what it uses. So I'm writing to address 44 here, and I'll write some data. So let's just write some random data. So I'm going to write a 5C to it. Previous example that I ran. And so what I'm going to do is run the logic analyzer and the capture. So my display is showing D, so it's just doing mode. I am going to just keep overwriting the data. I'm going to call it log, same one. Yes, I want to replace it. The display goes into C mode, which you can't see on the screen. It's capturing. It shows me the map here that disappeared is showing on my display. I'm capturing. So now I'm going to do a read and a write. So I'll start my, and I guess I'll do a read of the device ID as well. So I will start running, write data, read data, and read the values. And it captured all of the data. Let's go here and stop the capture mode. 11 events, that looks about right. Display goes back to D mode. Let's open up the Excel file next to it. Let's see what it captured. All right. Oh, don't need the previous one. So here's my log. Don't need this. So if I come up to here, I wrote to address 34, which is going to take some translating to do here. So wrote to decimal address 34, which in hex is address 22, but that's the shifted address, not the unshifted address. So I'll have to do some translation on that. So you'll see here, back out first. So here's was my write, my read, and then my read the register command. Sorry, again, I don't have a scrolling mouse. The USB ports are used up. I don't, for all the test instruments. Okay, so remember what I wrote? I wrote a 5C to the device. Go back to this. So address 44, I wrote a 5C. Now the address 44C, as we said, was it's using a different format on the data capture. So I'm going to do it in shifted mode. The only thing that changes is that now the address shows up as 22, write acknowledge, acknowledge from the slave, wrote address, wrote data 5C. Let's see what my log file says. I wrote to 34, which again translates to address 22 here, wrote 92 in decimal. So let's see if that was the right data. So in decimal, wrote 92, and that ends up being 5C, and that's exactly what I wrote here. I wrote 5C, and this says I wrote 5C, so data logger agrees with that data. So I guess the data logger is decent for small packets of data that you're going to send that you could see on your display. As I showed before, sending large streams of data seem to have problems picking them all up. So this should be reading back my command. We'll do on the address translation. Again, I'm reading from address 22. I get a read acknowledge. I'm going to send out a read command. and then got an acknowledge, and I'm going to read data 5C, neck, and then a stop condition. So let's see if I caught that stop condition. So now I read, so that's different, using a different address, and then it's saying, should see the data coming back. I see a stop condition, but I don't see the data coming back 5C, which should have been a 92, so I don't see that coming back. Did not capture that. Maybe you have to spread them out more often or something. Not sure about that. And then let's see, so now it's saying to get the register data back, which was, I'm not sure what it's going to show up here, but to get this 000218, let's see what the logic analyzer says it actually copied or transmitted. All right, so much bigger sequence than it appears the data logger captured. So I'm going to write to address 7C, which going to the unshifted. So I wrote to F8 to find out F8 or 7C. Let me see if my data logger captures that anywhere. No, I did not. Oh, so we got to do 7C. So let's see. So 174. I'm sorry, 124. So I did write a 124. It said I got an acknowledge. And then I wrote 69, which 69 and decimal is a 45. So it did write a 45, so it's capturing that. Here's 124. It wrote a 69, data writes, purple. Now it's going to do a read at 124, which we said was address. So that's right. Now the data that it reads back should be a 0, which it got, a 0, a 2, and an 18. 0, 2, and the 18's missing. It then shows a stop. So capturing 1 or 2 bytes, it looks like the capture works good, but trying to capture long strings of data, not so good. I guess I would probably just use the logic analyzer rather than pulling out this controller, not being able to trust whether or not it is giving me the right data or not. Any questions? Let me know.
Hello, Roman Budek. So I'm still looking at this I2C driver board. Did actually find a useful case for using the display. And again, I'm using the FM Plus board to measure the I2C with soldered down devices. There's my board with the display. There's my computer and the GUI display. So the first thing that's interesting is the map is showing again all the hard coded devices. And I'm going to select to go into monitor mode. That causes the M now to show up on the display, and it'll show up all the traffic. So the first thing I'm going to do is go to this software here. I apologize, the video's kind of hopping around. I'm going to go to device 44, which is that soldered down device, and I'm going to pick some different data to write to. And I'm going to go over to display here. I'll hit the right button, and you'll see graphically what it's going to show on the display as it gets transmitted. So it captures that it did write to address 22, which is the 44 shifted, and the data I wrote was 76, and it in fact wrote 76. So now let's try to do a read command, and you'll notice the address now reads address 22, and the arrow above the 22 shows that it's a read versus a write, and it read back 75. What's interesting now is, remember when I went here and did the device ID read, the capture mode does not get all 3 bytes, it only gets 2. I'm going to go here on the screen and try to get the light out of the reflection out, and I'm going to do a read. You know, it's interesting, it writes 7C 000218. That is a 7C, not a 0. It is a 7C as in Charlie. And that is exactly what the data was on the logic analyzer, and that is the data that should be read back 000218. So the display, actually, if you're sending small packets, it's kind of useful to send the clock and data is accurate, graphically shown on the bottom, showing what it would look like for that data pattern. And the map is showing all of the accurate devices. So that's kind of neat to watch. And then, and I can match that up now with, let's go back to the screen here, to what the logic analyzer caught previously when I did to read the data, wrote to address 7C, which again you got to translate. In this case it's see, 7C is the shifted address, and it wrote 45 first, got an acknowledge, and then it read from address 7C0002. So if we look at the screen, we can see that in fact it did write to 7C, and then it read back from 7C the data, so it captures that whole string, which is kind of interesting to see. Let me go ahead and hit it again. Go back to the software here, and now I'll read the status ID again, and you can see that it did send it and then receive it again in the monitor mode. So for sending small data packets using the graphics and so forth, but when you start to send long data packets, it looks like they just get missed by the software. Anything else? Let me know. Hello, this is Roman Budek. I found a kind of cool application to have a NXP processor act as a I2C slave, and to be able to set it to any address that you want. And furthermore, the example allows it even to parse commands, so you could send commands and be able to interpret them, act as a slave device. Obviously, if you have your real device or sensor available, that's great. Maybe you were waiting for it to arrive, or you want to do some simple debugging and see if it's the sensor or if it's your code on your master. This will be an ideal way to troubleshoot it. So what I have is I have a LPC 804 board, and I like this board because smaller form factor. It's got nice legs on it. Makes a nice sturdy connection. What it also has, it has the nice connections for I2C right off the edge. They're labeled, as you can see if I zoom in here. S clock, data, ground, and VDD. I don't need VDD because they're going to be running at the same board, available off of a nice header. Pull-up resistors are on there, but I'm going to enable them on the monitor anyways. I'm going to use the I2C drive to be able to sniff the packets and actually write data to it. I'll be able to see the address show up, and then also traffic on the device, and be able to make entries with it. So a shout out goes out to this website here, which has a GitHub site which lists the software, and that was written by a gentleman from Adafruit, so I'll give him a shout out and a link to where to get the software. It was originally written for an LPC 845. It was fairly easy to convert. It took about a half hour to make it an 804 device, be able to rebuild it and compile it, and to be able to run it on this board. The 845 does not have pull-up resistors, doesn't have any other I2C. This 804 board also has a temperature sensor, so if you want to write to a hardwired device you can, or to write to the MCU, which will act as a slave. It has A to D conversion and so forth. On the device is showing a breakout board. Again, I'm using the 804, which is a little nicer form factor, I think, to use it. There's the address that you can configure, 7E. So the peripheral that I was trying to mimic is a 50 50, so it's fairly easy to go into the config file there and just change the address, and you're off and running. You do have to rebuild it, so it's not an entry that you enter. You have to rebuild and then download into debug. And then the nice part is the registry, which you can do. You can add in functions and have it respond back and act like a real device, so you can have it mimic. It's a very slick software was done. First one is who am I. You can enter, you'll write to a register 1 and read back. You'll get a value from it, and that's all programmable. You can also then do who am I. You write to register 1 version 02, and you would get back a 0A for version right now, or who am I, you get 45, and that's commands that you can enter A to D values as well, which I'm not using, but you can write to A to D and get status, and you could easily add other commands. So it's a very nice software example that you can act as a I2C slave, and that's again on GitHub. The software is available for it. So the I2C sniffer, I did hear back from the company, and they did have a way of making it run. Last couple times I tried to run it, you had to run multiple copies. Well, the suggestion was to put it on a command line and make it execute to the COM port. So right now it's a COM port 38, and have it run directly to COM 38. That comes up, and then it runs fairly nice after that. So thank you to them for responding and giving a nice suggestion on how to make it run by running it directly off the COM port. And so here's my device. It has not found my slave device yet because I haven't executed. Here's my code that I wrote for the rewrote it for the LPC 804 because that's the board I had. The config file here would show the address, so I've changed it to 7U. The commands are written under here in the source file, so when you do who am I, it comes back here, and if you look through the code, it tells you what response you expect back from the device. So it's going to respond back here with the 45. You could give whatever command you want. Version comes back here, and it responds back with the version number. It's hard-coded 0A that it's going to respond back. But so code does run very, very nice. I'll show you how that runs. And so I have it set up to use my command window here. So it's address 50 is what it's going to respond to. Again, the LM75 that's on the board. I can set jumpers for that. And so what do I see with my window here as well as on my device? I see the temperature sensor 50 is the device that I hard-coded, then I want to mimic with my MCU. The display, you can see, shows the same thing, showing that I'm reading and writing to the addresses. The LM is on the board as well, the temperature sensor. And so going back to these commands that we talked about, so I can go now to device 50, and if I write to register 01 first and then read back from it, so I'll write, and if I look at my screen, I can see that it wrote to address 50 over on the right hand side of the screen, and the triangles pointing to the right, meaning it wrote the data. And now I will go ahead and read the data, and it was, as expected, should be a 45 that it read back. And if I go to here, you can see that in fact I did read back a 45. You can see the arrow pointing to the left and showing me that from address 50 it read a 45. So it parsed the command. Now I will write to register 2 and read back the version number, which we said was hard-coded as a 0A. So first I write to address 02. Doesn't show me there, but on my screen you can see it wrote to address 02. I will come back here and do a read from address 2, and it read back a 0A, which is what was hard-coded into the command, and it read back a 0A. So again, very nice parsing command, very nice software. Shout out to the Adafruit gentleman that wrote that. And now if I put in an invalid on my screen over here in the back is my console. It's been all valid parsing. If I put in an invalid command, it would go ahead and notify me and tell me that it is not a valid command. So I'll put in 22, which I know will go through the list of commands not found, and it comes back and it says unsupported opcode 22. So very nice software, and this should help with debugging I2C devices and having it act as whatever slave you require. Any other questions? Let me know.